Okay, let's continue with this case and let's move now to the unsteady simulation. So open the quartz mesh. Let's work with the quartz mesh. So you go to the case and you know where do you extract. So in this case, quartz, and go to Urans directory and open the case setup. So this is just the case setup. We have everything. So let's go through this case. So general, see that now we change to transient formulation. So the turbulence model, we're using k omega st, but feel free to use any model. We know what we're doing. We have addressed all the theory. Okay, but in this case, we are going to run Urans, so stay within spiral matters k epsilon k omega, okay? Or probably Reynolds stress also. Nothing else here. Materials, everything remains the same. Boundary cell zones and boundary conditions also remain unaffected. Reference values again remains unaffected. Now we move to the methods. So here is a little bit different from the steady solvers. Okay, here. Just give me a minute. Okay, so here we have access to the transient solver. So by default, Fluent now is not proposing the couple. So again, you have the couple, but I want to remind you that the couple is very computational expensive. So it's worth using it if you're working with the steady solution. For unsteady solutions, it's not recommended. Okay, it will slow down their computation. If you want, you can do your benchmarking, but you will realize that. So it's stay within this family of solvers, disaggregated solvers. Okay, so of all these, probably the best one will be the piezo. Okay, so use default options, and here transient formulation. Remember that now we want good temporal accuracy. Okay, so for the case that we're going to run Urans, this will not be a problem, but as soon as we move to SRS, it is compulsory to stay in second order, and even better bounded to avoid oscillations. Okay, the same will be for these variables, and actually unless probably unless you have these variables, in this maybe you will have it. So here would be better to go everything in second order. So just to exercise that in SRS everything must be second order. So put everything second order here. Here stay second order implicit or also unbounded. But for Urans, remember you can use these default values with no problem. Okay, so go pizza again, put everything second order. Second order, okay, for this small exercise that we're going to do. Controls, nothing to change here. Default values are okay. Report definition. So here now we have new report definition. So remember that now also we have a CFL number. So I have a monitor for CFL. And remember that now we want to probe the solution, sample the solution in many locations. So see that I added many probes here, okay? So if we look at the mesh, now I will show you those probes. Okay, look at all these points represent those probes. Okay, so see that in different points I want to sample velocity, pressure, or whatever, and then I can use that information to have my energy spectrum. There are also some lines that I put there that we can do some sampling there. So see that I put many lines there. So this is the thing when you go on a steady and you're doing things in the right way, you need to add before running the simulation, starting simulation, you need to add all these points, okay, and start to sample the solution. Also might be a good idea to add these points in also in other locations, okay, so you can get different in different regions. You can do your sampling. So we have all those points, and those points will all enable here. So if you open probes, you see that all those points, and in a single file I will save all that information. So I will have one for velocity component U, V, W, and pressure. And then you just can plot that information as we have done during the previous exercise. The monitors, nothing to do here, okay, stay as they are. One thing that in monitors here, this one is not necessary anymore. So when you are on a steady, this is not necessarily this one. You can add it for a steady simulation. On a steady, you don't need it. You can disable. We can initialize, okay. So now that we have an initialization, we can run. But remember that we have a solution previously for the steady, so why not using that solution? So let's interpolate that solution, and I will go here, interpolate, and read data, and you choose your case. So you have one in quart, fine mesh, it's up to you, okay? You can even take it from the fine. I will do it from the fine mesh. It makes no sense now going from finer to quartz, but you can do it with no problem. And I will use the simple solution, the one I know I have some nice fluctuation. Now see, it was interpolated, and you can go here, contours, and let's see what we have. So this is the field that we're interpolating, okay? And remember that when you are here, as you go here in solve initialize, you can add the fluctuation. So if you want to add another stochastic fluctuation to have something nicer, you can go init. By the way, this option is only available with the runs solvers. If you go to less, it's not available anymore. So you need to do everything in a setup of the runs, and then you can switch to the less. You put it there. You add your stochastic fill, and see that we add some noise. Okay. So now that we have this, let's, before running, let's save, and I call it piso 1. Okay. So we have initialization, we have everything, and in the methods, by the way, now we're using the piso. There are some other options. For instance, you can choose here the nita, non-iterative. So this use another method that you don't need to do the subcycling. Now we're going to do subcycling. You are going to see that. And the nita in theory is much faster, but however, you need to be careful that your CFL number must be less than 1 to have good accuracy. Instead, when using the iterative like this one, you can go with large CFL number, and then by adding sub iterations, you will guarantee that you will converge the solution within every single time step. We're going to see that in action, okay? So we go here, run, and we can start to run. So remember that here, when we go here, there is no limit. It's up to you. You need to sample the solution. You need to see your signal. Okay, we have done that. So let's run. In this case, let me show you if we have some solutions here. Okay, so for instance, here, this is CFL1, and see that in about, starting from the perturbative field, already in about 6 seconds, you will have enough statistic. However, I run this case up to 20 seconds. Okay, so it's up to you. For our purpose, let's say for the next time we meet, let's have something about 6 seconds, okay? You can have enough statistics. So let me show you all. You have all here, okay? And we're going to save the solution as well to do some post-processing. I will show you how to do that. So now that we have here, our goal now is to choose a time step. So remember, ideally CFL, if 1, that will guarantee good accuracy. But if you have a CFL larger than 1, it's also possible you are advanced faster, but you might lose some information in your solution. So here, we need to choose that one, and that is the tricky part. So usually you start with a small time step. Okay, let's put this value here, and you launch the simulation, you monitor your CFL, and then you see if you can go all, you can go down, okay, but just by monitoring the CFL. That's why we added that monitor there. So I will run. Also, as well, you can give the maximum time that you can run. So you can run this many times, or you can go here and in the text user interface, max flow time, and you say run up to 20 seconds, let's say. So automatically will stop when you reach 20 seconds. So what else we need to show you? Important that now also you need to save your solution every now and then. So as you go into calculation activity, see here that edit, and I'm saving every 500 time step. You have the option to put flow time, so you can say save every 0.5 seconds. And how many files, the name of the file, and how many files do you want to retain. So if you disable this one, you will retain every file every 0.5 seconds. So you can use those files to plot your solution, do your animation. However, as I mentioned previously, I don't like to use the Fluent files. I prefer to use inside files, okay? That one, you can set up that here, but before setting up that, we need to just check the time step if we have the correct level, because we need to give a saving frequency. So let me go run, and let's run the calculation and see and monitor all our quantities. So see that here where our first time step, usually the first time step, the first 10 or 20, it will take longer to convert. That is perfectly normal. And then slowly it will accelerate. By the way, also remember that now we're on Unsteady. Do not forget to enable your statistics, okay? So now we're sampling our statistics. So see that first iteration, it didn't converge. It's doing, see here that here we can say the maximum number of iteration per time step. So usually 20 is a good value. You can put a larger value, but 20 is already too much. So if you're running and it's taking 20, it might be a good idea to reduce your time step. Okay, in this case it's taken, but remember, initial iterations, it will take longer to converge. Okay, so let's wait a little bit while we get something. So see that our CFL is relatively low, 0.06. Okay, so this means that we can increase it, but still we need to wait a little bit more, no, while all my velocities, everything stabilize, and see our residuals. So what is happening here is that this is one time step. It's iterating and then reaching your convergence criteria, and then it will move. Okay, so I see a problem here. Just let me stop, because it should stop. So I think in the residuals I have enabled a very low value somewhere. So let me go back residuals. Okay, okay. So let me let me reopen the original case. Okay, the piezo one. So this happened when I enabled the NITA auction. It changed my tolerances, so be careful with that also. When you save a piezo and then you enable the NITA, be careful, because it will enable some other auctions here. So now you see that it will converge 10 to the -3, okay? And we have everything set here. So I will let's put it here, okay? We have that, and let me run. So just to make it clear, let me save another file. I will call it piezo, now I will call it NITA1. So if I go NITA1, and if you enable this, you will see that, sorry, you still piezo. Enable this one. You enable some other auctions. So as you go here in monitors, see that you can select this one anymore. You need to access that information somewhere else. Okay, so be careful, because if you do it, I don't know why, at least in my version, I cannot go back to the original piezo, so have a backup piezo NITA. Okay, so usually the convergence criteria of the NITA are much lower than the piezo, and that's why it was taking longer. So now let me choose the piezo. Okay, so the piezo is right. Okay, we have also the data, I think. Okay, have also the data, the initial condition, we need it. And let's be sure then. Okay, yes, this is the perturbative field, everything. So let's start from here. Okay, run calculation. We have, let me reduce it a little bit. And see that you disable the statistic there. Okay, so always enable your statistics. So the point here is that we're starting from the steady solution that is already converged. You have some fields, so you are going to speed up your computation. Let me show you. If we look here, look at that. We have left with initialization, right no is an initialization. So see that here, and it's starting from initial field, and I will speed up my computation. So if I let it run, see that you can save a lot of time by just using an initialization. It doesn't need to be a perfect one. It just needs to be a field that is somehow perturbed. And see that the one that started with from 0, it took longer. So it's not 3 seconds. You see that maybe in 3 seconds you see some vertical structure, but still you need to let it run a little bit to so it can stabilize. So probably it's like 5 or 6 seconds to the point that it's stable. And something that probably in this case it will be fast, but if you have meshes about 20 million cells, this initial transient of 4 or 5 seconds can translate maybe in a couple of days of simulation. So that's why we start from a steady simulation, maybe quartz mesh, then interpolate, or even a fine mesh in a runs. You can go fast. Okay, so this is the less simulation, by the way. Okay, so we have. Let me reduce this side there, and I press calculate. I have everything. We have time. Here it's asking the residuals, no, overwrite everything. So remember, as you go back to the directory where you have that, see that you were going to have many files. See that now you have the U file. As you open this file, you will have all the information of these probes. Okay, so you know the coordinates. You can go back and interrogate the case files, and you will see there the coordinates. And you can extract your information from there. So see that here it converges in about, let's say, almost 20 iterations, which is too much, but slowly it will get faster. Okay, so as we look here, we're going to see the proper behavior. And this point is just waiting. So you need to monitor quantity, CD, CL, see when the solution is statistically steady from a turbulent point of view. And then you can say, okay, I will stop here. So let's this solution run, and let's see what we have. So see that now it is converging faster. So see that now initially it was taking 20, now it's taking 9 and so on, and then it will be 8, and in one point probably will be 5 or 4. So ideally when you're running this segregated solid piso in eta mode, not the neta, you should aim for a convergence between 4 and 8 iterations. So if you're converging between 4 and 8, that is a good value. Okay, that also is telling you that you can increase your CFL number. So as you check here, you have it here, CFL max. So okay, in this case it didn't take the modification we had. Okay, so see that 0.7, so this is good accuracy, but we can go larger in the CFL number with no problem. So as you go larger, you can advance faster, but you might lose some information in the solution. So I will let this simulation run a little bit, and let's see what happens later. Okay, we're back. So see that after a while, it's taking just 4 iterations to converge. So this is ideal. This is what you should aim. However, you see that your CFL is 0.7, so you can still increase. So let's do some experiment. So let me go stop here, and let me double this number here. Okay, let me see that. So now I will see a jump here, but also in all my quantities due to the fact that we're increasing the time step, and it also is likely that it will take longer to converge. However, see that now it will take your time you will advance much faster. So this will be a compromise. If you want accuracy or you want to go fast, this is something that you can do because we are on URANs. There is no problem, unless this is something very delicate, and unless you should have a single time step, you shouldn't play with your time step. So let's go calculate now. So immediately see that now we see that it's taking longer to converge. Still is within that value now, 0.48 iterations. And see the CFL, it is double. Okay, it's almost proportional. You double here, you double your CFL number. And still we can go higher. So let's go and put it 0.5. Okay, so I will advance more faster here. Okay, again we're going to see another jump in residuals. Will take longer to converge. Probably we're almost in the limit, but see that your CFL now is larger, so meaning that you will advance much faster, but also it taking more iterations. So this is kind of a compromise. So previously you were 0.001 taking 4 iterations. Now you are 0.005 is taking 10 iterations. So in this case, it might seem that it's a good choice this one, because at the end you will have almost the same number of iterations, total iterations, to reach a certain level. But sometimes it might happen that it chooses times that too large, the number of iterations will increase a lot, so it's not economical. It's not viable from an economical point of view, from the point of view of the computing time. So you should monitor always this and get your budget and see if it works. So you will see that now. You see that now it's taking about 10 iterations. So at this level it was about 4 iterations. At this level is 10 iterations. So at the end of the day, you will see that to reach the same final time, we are going to have about the same number of iterations. Okay, so it is a good compromise to go here and put this CFL. But if I stop now, and now I will go 0.01, so you press enter a couple of times there to just be sure that you are inserting that data. See that we have sampled this information there, and you press now calculate. We see a jump in the residuals, but also you will see that it will take longer to iterate. Okay, or 13 iterations. Your CFL is becoming 8, something about 8. So the methods implemented in Fluent, they are implicit. So the theory tells that implicit methods are unconditionally stable. Okay, so meaning that you can use any CFL number and they will be stable. But the fact that you can use any CFL number doesn't mean that your solution will be good or that it won't diverge. Eventually, very large times you will diverge because you're missing completely the physics. Okay, so all the time is a compromise. Okay, I have been able to run up to a CFL of 50, but I know that my solution, I'm missing a lot of information. But my goal was to advance fast, okay, to get some periods, to determine some periods of my solution. And then also you advance fast, and at one point when you are ready to do the sample, that you are going to start to get your good quality simulation, you just stop there, reduce your time step, and start to do your correct sampling there. So see, you start to run that one, you will see that to reach this time here, it took probably like 5 minutes. To reach this time here now, it was really fast. Okay, you see that advance larger times that you will advance in physical time much faster. And see that we're kind of capturing some unsteadiness there. It's taking about 14 iterations, so it will be a compromise. Okay, so initially here was 4 iterations, and now it will be 14, but you are running at time set that is 10 times higher. Okay, so yeah, it's a compromise. Now you go 4 iterations, you multiply times 40, so it's still, from the computing time of your computational point of view, it works to use this CFL number. Still, it will be faster than using a small 1 × 10⁻³ So my math was this one. So here it was taking 4 iterations now, and here it's taking 14 iterations. Okay, so here is you multiply by 10, which is the factor that I'm increasing from here to here is a factor of 10. This one will be 40 and this one here we have 14, okay, meaning as this is lowest, and this one here is economical, okay, it works. So to reach the same time here, it will take 40 iterations, here 14 iterations for that time. Okay, so again, let's wait a little bit. Let's see what happened in 1 second. Okay, so it will take a while, I know, 5-10 minutes, and let's see you later. Okay, we have about 1 second of simulation using this time step, 10 to the minus 2. As you see, in my case, 4 cores was relatively fast, like, I don't know, 10 minutes. So you can get an idea how long it will take to get to 6 or 10 seconds, okay? So using a large time step is fast, then you will see that you reduce it by an order of magnitude, it will take much longer. So it's up to you. You can get your budget easily by looking at the number of iterations. But in general, your goals should be not to take more than 20 iterations, even for large times, okay? More than 20 start to become expensive. So at this point, let's do, okay, now that we maybe have an idea of a frequency, okay? So see that here we have a period kind of in this. So now that we have an idea, let me stop it there. We can go back to plots, FFT, and let's do some signal processing. And here in plots, FFT, so we can take a look at the input files. See that in the directory where you are running, you are saving all the files, so you can access that. And in particular, I want to access CL, is the one plot. And we have this time signals, okay? So let me click to branch and let me go to 0.6. And see that your period, let me make it smaller, larger, sorry. So you will have a period of about like 0.5 seconds, 0.6 seconds. So the idea of knowing a period is that you can now have an idea of your maximum time step. So it's clear that if you choose a time step about 0.5, you are missing the whole information. So see that still we're much lower than that, okay? And again, in the sense you see choose 0.2 is not large enough to resolve well this period. So we are at 0.01, the largest one. So meaning that if your period is 0.5, you are taking 50 points to resolve, which is good. Let's say that the absolute maximum of point or minimum of point that you need to resolve the period will be something about 30, your time step. We are 0.5, 0.01 was okay, and the one 0.01, it was even better. You are doing a much better sample. But also this is telling us that now we're going to save the solution, just to show you that you're saving frequency, okay? So if you want to save your solution to do the animation, the plot and everything, okay, you will need at least, let's say, 10. If you want to plot everything and see the animation, full animation, let's say, as I mentioned, so like 30, but for us to save the files, because those files, that is a lot data, we can say that let me save with a frequency of 0.05, okay? So 0.5 will be, so like 10, we're going to save about 10 steps here, and this is we're going to animate that. So that means that here I would save every 0.05, okay? So to save the solution, now you are going to go here, calculation activities. So see that you can save that already here. In time step, you can say save it every 0.05. You disable this and it will save the Fluent file, but as I mentioned, I don't like to use those Fluent files. So let's put here every 0.5 and only keep the last two files. But as you go here, automatic export, solution data, here you can save in different formats. So see that you have all these formats available. Personally speaking, I really like this one, inside case goal. Okay, we can export this one and then open it in ParaView, or if you have access to Insight, which is a very good visualizer now for scientific computing, you can use that one. But let's use this one, okay? Then you give it a name to the file that you want to save. Okay, I usually call it like this. Time step. So some other format will give you the option to save every given time. This one only gives you the option time step, but we know already that if you put 5 there with a time step of 0.5, 0.01, it will give you this saving frequency that we were aiming of 0.05. Save in binary is the null center or solve center. It's up to you. Usually I like to put it null center. And here, deselect this one means that you are going to have single files for each field. And then here, select all the fields that you want to visualize to save to output. Okay, so remember, the more fields that you are selecting, the larger those files will be. So you see that now you are accumulating a lot of data. Okay, so be careful of your hard drive space, or if you really need all this data. So in this case, I will keep it to the minimum. Okay, so I will save this and this tree, and also maybe the Q criterion. Okay, then you have statistics. See that we're computing statistics. You have these 2 custom fields also. So it's up to you, where I will keep it to the minimum. Okay, every now and then save. So I would call it PC2. Okay, and now let's run another one, 0 to 1.5. Okay, so let's say that max flow time 1.5. Okay, and we're going to save a few files, and then we're going to, so we have done everything for the Unsteady. Okay, so as you go here, let's skip this same time step. We're going to save the files, then we're going to have those files that we're going to open it later. But then after we save those files, just to show you, we can go back and reduce this CFL number. You're going to see the difference, but in theory, by reducing this to getting a lower CFL number, we're going to improve the solution. Okay, so calculate, and let's wait a little bit until we arrive to 1.5 seconds. Okay, so in my case, arrived to 1.5 seconds. So see that kind of start to see the periodic behavior, no? That is maybe reaching, or you might reach statistically steady behavior. So if you take a look at your folder where you are running, see that here you have these new files. These are the files that we're going to use for the post-processing. Okay, so you see that here you're saving those fields that you chose, and see that those files can become really large. If you have a very large mesh, they can take a lot of space. So be careful about what you save, frequency saving, and everything. So that's why we run initially. We got an idea of time step, periods, and everything. So at this point we're running. I hope you get the idea. So if I go here and I reduce my time step, whatever I do by reducing the time space, just improving the solution, but it will take longer. Okay, so just to make clear this concept, so let me put it here. Okay, so I reached the time 1.5, so I need just to increase it here. Not full time, just put it back to 20. Okay, so by reducing the time step, as you look here, your iterative convergence. Okay, so at the beginning, every change will take longer, but see that it is going faster. Okay, so maybe it would be a good idea also to increase the saving frequency of the files, you know, because now we're saving every 0.005. You know? So what you can do, go back to the activities and just multiply by 50. Okay, I won't do it, but you got the idea. But see that it's going faster. Okay. And you get the point that I was telling about the CFL, that now to reach this time here, you just measure the clock time from here to here using CFL 10, and probably here it took 10 minutes or 20 minutes to reach to do the same period, but this time it probably will take 1 hour or more. Okay, so you see that it's still affordable and it's still within the 20 iterations limit. So it was using the CFL of 0.01 because also it was resolving well your frequencies. Okay, so these are things that you need to take into consideration at this level when you are doing URAN. When you move for less scale resolving, there your CFL is highly recommended to keep it at 1, less than 1. Probably the maximum will be 2. So at this point, let me stop this one here. Okay, you get the idea. You can save everything. You can visualize your fields. Then we're going to visualize the fields. And just to mention something, that here I upload some inside files now that we have 1 second of sampling. So download that one. Okay, will be the same case with a different frequency and more files. So it's exactly the same that we were saving, but you can download this one, and the next tutorial we are going to open this file, okay, and do the post-processing with ParaView. So just to show you, I will stop here, and just to show you about the NITA that we have there. So you can go, no, I won't save. Remember that we have a NITA case. Okay, we need the data file. Okay, you can use the previous one for P. So okay, but that's inside. That's no problem. Remove. Okay, so okay, that was telling me to remove the inside case that we have. Okay, in your case, if you want to keep it, just don't remove it, because I know that I don't need it. So we're going to use the NITA, starting down in the piso. So remember that in NITA, you go here, non-iterative, okay, then piso, you have 2 options, okay, so you can play around with bias, but that's used, for instance, the piso one. Okay, the idea is the NITA is it is not going to do, you see that here you have the inner iteration, it's not doing those iterations. Okay, so let's run, but it will be much faster. We're going to see that. Okay, so let's run. Okay, no, override everything. So it's not doing all these 20 or 5 or 4 iterations. In this case, it's just one single iteration that it will be converged. This is not the problem with the NITA. Sometimes it's very difficult to assess if it is converging well. Okay, so usually it will converge well if you keep your CFL number below 1. Okay, so usually NITA is done for this kind of simulations that you already that you have a CFL less than 1. You know that you are going to do your sampling right away with low CFL numbers, and usually it will give you a good convergence. See here that it's converging very well in just 1 iteration. Instead, for the previous one, it was taking 4, 5, 10 iterations. Okay, so as you increase the time step here, it will still run, but you are going to lose a lot of accuracy. But you can already see that it's much faster. It's advancing much faster. So usually for less, this is the recommended method. Usually in less, we're keeping a low CFL number, so this one is recommended. It advances much faster, and it have also some implementations that you can accelerate even more your solution. But I guess it's quite clear that it's advancing faster than the other one. So let's let it run for a while. Let's let it run up to 0.5 seconds. Okay, so it was relatively fast. And yes, so see you later, and we will just take a look at this, okay? Okay, I have reached about 0.5 seconds of simulation, so I will stop here. So I hope you got the idea of the non-iterative advancement. So this one is used basically when you are sure that you want to use a CFL less than 1. Okay, so the idea basically probably this will be equivalent to the PISO in iterative advancement, but with one iteration. But the piece of one iteration, it has problem or converging. Instead, this one they need to have some improvement that it will have a better convergence in comparison to the piso eta. You have another formulation here, the fractional step, very similar, okay, with some improvement, okay, in the convergence. So this one use one iteration, but be careful to have your CFL less than 1 just to have a good convergence. So you have been running samples, so now you see that we can have an idea how long it will take if you use CFL1 or if you go CFL2. So what I will do here, just to show you, already have in the files. Also, you have in the website, you have some time series. This time series correspond to 2 cases, okay? These are less cases now, but pretty much will be the same regarding time for CFL 1 and 10. And see that it's clearly that there is a difference in the mean values, and the CFL 10 probably is over predicting a little bit more. However, it's also capturing some frequencies very well, also the leaf signal, okay? However, for good accuracy, we know that we want the signal with the CFL1. And just to show you that both of them are capturing the frequencies, dominant frequencies, if I do the frequency analysis, okay, I look at the leaf signal, see that both signals are pretty much the same value. This was the leaf, and for drag it's a little bit different, but again, see similar peaks, okay? So as you can see, it managed to capture the same frequency. If you choose a time step too large that you miss the frequencies, you won't be able to see the peaks in your frequency analysis. Okay, but we know that 0.01 is still is okay. So let's do the same analysis. So I have the signals in the time series. You can open those here. You go FFT, okay, and you can go here, low input file, and let me open. So basically here I have a time signal for an URAN simulation, okay, so no delays. Okay, and let me plot the signal here. So this is the signal. You can compute, I can subtract both. Subtract, I don't need, click to branch, and let me go from. So we can do the traditional analysis to see when it's becoming statistically steady. You can get all your statistics here, okay? You can do all your normal analysis of this signal. And you can also plot your power spectral density function. So let me go in axis. So I put log there, and log there. We get this plot, okay? So if we superimpose here the -5 surge, probably here you will see that this one there is a change in the slopes on some frequencies. So probably this is not resolving very well. We have this large, I think this, yeah, no, it's 1, okay? But everything is being modeled, okay? So you can do your traditional analysis here. Always remember you have that capability. And also let's post-process the data, because now we run that one, you will get the fields again, you get L0, and see that it's very different what we have. Now we have the actual vortex shedding. You can get RL, and see that this one, since that the values are much lower than 5. Okay, and just to remind you that we are working in the quartz mesh. Okay, so see that it's telling that probably the largest vortex is resolving, but you have the others that it's not resolving well. So again, this is the quartz mesh. As you move and do the same with the fine mesh, you will get much better results. Okay, so let me adjust here. So it displays there. And for instance, you can also get in surfaces the Q criterion, isosurface, and the domain, velocity, Q criterion, compute. Okay, let's put 100. And let's plot. You should have it here. I don't want that. And actually I don't want to see the couplings. And see there you have the vortices. And already you see that kind of some stretching. Okay, so this was this case, the Unsteady. So I will stop here. You got the idea how to do everything. So you let it run by probably some 5 seconds, or probably 8 seconds, you can do it. You will get enough statistics, but also save the last time step, interpolate, say the interpolation file, and we can switch back to define mesh with ls and try to run ls in that mesh. Okay, so with this I will stop here. The next tutorial we are going to open the Insight files to do the post-processing in Parabium. See you next one.